In the quiet scale far below everyday experience, where size loses its familiar meaning and matter behaves in ways that seem almost dreamlike, the electron appears as one of nature's most essential presences. It does not announce itself loudly. It cannot be seen with ordinary light, cannot be touched, cannot be divided into visible pieces. Yet it is everywhere, woven into the structure of every object, every living thing, every grain of dust drifting through a beam of sunlight. To understand the electron as a fundamental particle is to step into a story about how deeply scientists have looked into reality, and how, at a certain depth, the search for smaller parts seems to pause in a kind of elegant stillness. For centuries, people wondered what everything was made of. Early thinkers imagined matter could be divided again and again, like breaking stones into pebbles, pebbles into sand, sand into finer grains. Eventually, science gave this intuition a name, the atom, meaning indivisible. But as knowledge grew, even atoms were found to have inner structure, a dense nucleus at the center and lighter components surrounding it. Among these components, the electron emerged as a distinct entity, carrying electric charge and playing a crucial role in shaping how atoms interact, how light is produced, and how chemistry unfolds. When we call the electron fundamental, we mean that, as far as all experiments can tell, it has no smaller pieces inside it. It is not built from tinier blocks. This idea did not come easily. Scientists have a long history of discovering that supposedly basic things are actually made of something deeper. Molecules were once thought fundamental until atoms were revealed. Atoms seemed final until protons, neutrons, and electrons were discovered. Protons and neutrons themselves turned out to be made of quarks. Each time, the curtain was pulled back to reveal another layer of structure. Naturally, physicists asked whether electrons might also hide inner components. To answer that, they designed experiments of extraordinary precision. They collided particles at immense energies, using vast machines that accelerate beams to nearly the speed of light. By smashing particles together and studying how they scatter, scientists can infer whether something has size or internal structure. If an object contains smaller parts, high-energy probes tend to reveal patterns, irregularities, or signs of substructure. But again and again, the electron behaves as if it were point-like, with no measurable size and no internal features. Within the limits of today's technology, it appears structureless. This does not mean the electron is simple in every sense. Its simplicity lies in its indivisibility, not in a lack of rich behavior. The electron has properties that are precise and unchanging across the universe. Every electron has exactly the same electric charge, a fixed negative value. Every electron has the same mass. Every electron shares a quantum property called spin, which influences how it interacts with magnetic fields and how it fits into the structure of atoms. No matter where an electron is found in a distant galaxy, in a lightning bolt, or in a neuron in the human brain, it is identical to every other electron. This perfect uniformity is one of the quiet signatures of something fundamental. In modern physics, the electron is described within a framework known as the Standard Model, a theory that organizes the known fundamental particles and their interactions. In this view, the electron belongs to a family called leptons. Unlike protons and neutrons, which are made of quarks bound together, leptons show no evidence of internal composition. The electron is the lightest charged lepton, and its stability is remarkable. It does not decay into smaller particles. Left alone, an electron is expected to exist indefinitely, a persistent thread in the fabric of reality. The idea of a fundamental particle also shifts how we imagine what made of means. In everyday life, being made of something implies pieces arranged together. But at the quantum level, the concept becomes subtler. The electron is not a tiny solid bead with a surface and interior. Instead, it is better understood as an excitation of an underlying field. According to quantum field theory, the universe is permeated by fields corresponding to each type of fundamental particle. The electron field exists everywhere, even in regions we consider empty space. What we call an electron is a localized vibration, a stable pattern of energy in this field. In this sense, the electron is fundamental not because it is a miniature object built from parts, but because it is a basic mode of the universe's structure. Asking what it is made of may be like asking what a musical note is made of. A note arises from a vibration in air or in a string. It is not assembled from smaller notes. Similarly, the electron arises from the properties of its field. It is a manifestation of the field's existence, a quantum of that field's energy. The fundamental nature of the electron also shapes the architecture of matter. In atoms, electrons occupy regions around the nucleus in patterns determined by quantum rules. These patterns are not arbitrary. They arise from the electron's wave, like behavior and its interactions with electric forces. Because electrons are fundamental and identical, the rules governing them are universal. This universality leads to the periodic table of elements, to chemical bonds, to the stability of molecules. The solidity of a table, the fluidity of water, the complexity of DNA all depend on electrons following the same underlying principles everywhere. The concept of fundamentality also carries a sense of boundary. It marks the edge of our current understanding, the place where explanation shifts from made of smaller things to described by fundamental laws. For the electron, those laws involve quantum mechanics and relativity, woven together in precise mathematical form. These laws do not explain the electron by reducing it to parts. Instead, they describe how it behaves, how it interacts, and how it contributes to the larger patterns of the universe. Still, science remains open to the possibility that deeper layers might exist. The history of physics encourages humility. Future discoveries could reveal that the electron has substructure at scales even smaller than we can currently probe. Yet any such structure would have to be extraordinarily subtle, because all existing evidence points to the electron acting as a point-like fundamental entity. For now, it stands as one of the simplest building blocks we know. There is something quietly profound in this. A fundamental particle like the electron represents a kind of endpoint in the chain of composition. It suggests that the universe, beneath its immense complexity, may rest on a small set of basic ingredients, governed by consistent laws. From these ingredients, everything else emerges: stars, planets, life, thought. The electron, tiny beyond imagination, participates in all of it. When we consider the electron as fundamental, we are also touching on the limits of language. Words like particle, object, and thing come from a world of solid forms and clear boundaries. The electron does not fully fit these categories. It is described by probabilities, by wave functions, by fields. Yet calling it fundamental acknowledges that, within our best theories, it is not composed of smaller constituents. It is a primary element of the physical story. In the end, the electron's fundamentality is both a scientific conclusion and an invitation. It tells us how far we have traced the layers of matter, and it hints at the deep simplicity underlying the visible world. Beneath the variety of shapes, colors, and textures, beneath the motion of living systems and the glow of distant galaxies, the same kind of entity moves and interacts. The electron, indivisible in our measurements, constant in its properties, and essential in its role, stands as one of the quiet foundations of reality, a basic note in the vast, unfolding symphony of the universe. When we gently follow the question of whether the electron has any inner pieces, we drift into one of the most delicate frontiers of modern science. The idea that something might have no internal structure at all can feel unfamiliar, because in everyday life everything we know seems built from parts. A book is made of pages, pages from fibers, fibers from molecules. Even the smallest speck of dust, if examined closely enough, reveals layers within layers. So when physics suggests that the electron may have no known internal structure, it invites us to imagine a level of nature where the familiar pattern of something inside something no longer applies. The journey toward this understanding unfolded slowly. After the electron was identified as a distinct particle, scientists naturally assumed it might resemble a tiny version of larger objects, perhaps with size, shape, or internal components. Early models sometimes pictured it as a small sphere of charge, but as experimental methods improved, these images began to fade. The more precisely electrons were studied, the less evidence appeared for any spatial extent or internal features. Instead of behaving like little balls, electrons responded to probes as if they were point-like, with no measurable radius. To test for structure, physicists use scattering experiments. These involve directing high-energy particles at a target and observing how they deflect. If the target particle has inner parts, the pattern of deflection can reveal clues, much like bouncing marbles off a cluster of smaller objects, produces a different pattern than bouncing them off a single smooth bead. Over decades, increasingly powerful accelerators have been used to probe the electron at smaller and smaller scales. Yet no deviation from point-like behavior has been found. Within the reach of present experiments, the electron shows no sign of substructure. This does not mean scientists claim absolute certainty that the electron has no inner structure. Rather, they say no known internal structure has been detected. There is an important difference. Science always leaves room for future discoveries. The phrase reflects both confidence in current evidence and openness to revision. Still, the limits reached so far are astonishingly small. If the electron does have size or components, they must exist at scales far beyond what we can currently resolve. The absence of observed structure also aligns with the theoretical framework used to describe electrons. In quantum field theory, the electron is not treated as a composite object. It is represented as an elementary excitation of a fundamental field. This means the theory does not include smaller building blocks inside it. The equations that successfully predict experimental outcomes assume the electron is basic. If hidden structure existed at accessible scales, the theory's predictions would likely show discrepancies. Instead, predictions and measurements agree with remarkable precision. One of the ways scientists check for internal structure is by measuring the electron's magnetic properties. The electron has a magnetic moment related to its spin and charge. Theoretical calculations of this property, based on the assumption that the electron is fundamental, match experimental measurements to an extraordinary number of decimal places. If the electron had internal parts influencing its behavior, subtle differences might appear. So far, none have been observed within experimental uncertainty. This agreement is one of the quiet triumphs of modern physics and a strong hint that the electron lacks substructure at measurable scales. Another line of evidence comes from how electrons behave in high-energy collisions. When composite particles, like protons, are smashed together, the collisions reveal their inner quarks and the complex dynamics between them. The outcomes show jets and patterns reflecting the proton's internal makeup. Electrons, by contrast, do not display such complexity. Their interactions look simpler, consistent with point-like particles rather than objects made of smaller constituents. The idea of no internal structure also changes how we picture size. In ordinary terms, having size means occupying a region with boundaries. But for electrons, attempts to assign a classical size run into trouble. If one tries to imagine the electron's charge spread over a small sphere, the energy required to hold that charge together would be enormous and inconsistent with observations. The quantum description avoids this by not treating the electron as a charged sphere at all. Instead, its properties arise from the behavior of the underlying field, and the notion of a tiny surface enclosing parts becomes unnecessary. This absence of structure connects to a deeper theme in physics, the search for fundamental simplicity. As scientists peel back layers of matter, they hope to find patterns that are not endlessly nested, but rest on basic principles. The electron, with no known internal components, represents such a principle. Its behavior can be described without referring to smaller pieces, only to interactions with other fields and particles. Yet the question remains open at the edges. Some theoretical ideas suggest that at unimaginably small scales, new physics might appear. There could be substructure beyond current reach, or the electron might be connected to deeper entities in ways not yet understood. But any such structure would have to preserve the electron's observed properties with extreme precision. That requirement makes speculative inner layers increasingly constrained. There is also a philosophical softness to this topic. The phrase, "no known internal structure," reminds us that knowledge is always provisional. It marks the boundary between what has been observed and what remains possible. It expresses a kind of scientific humility. The electron appears simple, but the universe has surprised us before. Still, in practical terms, treating the electron as structureless works extraordinarily well. It allows scientists to build technologies from semiconductors to lasers. It supports theories that explain chemistry, materials, and the behavior of light. The success of these applications reinforces the view that, for all measurable purposes, the electron behaves as a fundamental entity without inner parts. In the quiet perspective of documentary reflection, this can feel almost poetic. At the heart of matter, where we might expect endless complexity, we encounter something that, so far, resists further division. The electron does not reveal gears within gears or layers within layers. Instead, it stands as a simple participant in the grand interplay of fields and forces. This simplicity does not make the universe dull. On the contrary, from particles with no known internal structure arises the immense variety of forms we see. Complexity emerges not from intricate interiors of single particles, but from the ways these simple entities interact, combine, and organize under universal laws. The electron's apparent lack of substructure is part of that story, a reminder that richness can grow from fundamental simplicity. So when we say the electron has no known internal structure, we are describing the current edge of human insight. We are acknowledging the results of careful experiments, precise measurements, and powerful theories. We are also leaving space for future exploration. For now, the electron remains one of nature's simplest known building blocks, a point-like presence with no revealed inner pieces, quietly shaping the material world while keeping its deepest nature serene and undivided. In the gentle territory where modern physics meets the limits of imagination, the electron reveals a nature that refuses to stay in a single category. It does not behave only like a tiny speck of matter, nor only like a spread out ripple. Instead, it moves through experiments and equations with a dual character, sometimes showing the sharp presence of a particle, sometimes the soft extension of a wave. This wave-particle duality is not a trick of language, nor a confusion in measurement. It is a deep feature of reality, one that becomes especially vivid when we focus on the electron. In everyday life, the difference between a particle and a wave seems clear. A particle feels like a small object, localized, something that can be at one place at a time. A wave feels like a motion that spreads through space, like ripples on water or sound moving through air. These two ideas appear opposite. One suggests a tiny point, the other suggests something extended and flowing. Yet in the quantum world, the electron belongs to both descriptions, depending on how we look. The story began when scientists studied light and matter more closely than ever before. Light, long understood as a wave, sometimes behaved like a stream of particles. Matter, long pictured as made of solid particles, began to show wave-like effects. For electrons, this became dramatically clear in experiments that passed them through narrow openings. When a beam of electrons is directed at a barrier with two slits and a screen beyond, something remarkable happens. If electrons were only particles, we would expect them to pass through one slit or the other and form two clusters on the screen. But instead, an interference pattern appears, a series of light and dark bands, like the pattern made by overlapping water waves. This pattern shows that each electron is associated with a wave that can pass through both slits and interfere with itself. What makes this even more delicate is that electrons arrive at the screen one by one as localized impacts, like tiny dots appearing in different places. Each arrival looks particle-like, yet over time the accumulation of many such impacts forms the smooth interference pattern of a wave. The electron seems to travel as a wave, exploring multiple paths, and then appear as a particle at the moment of detection. Both aspects are necessary to describe what is observed. To make sense of this, physics uses the idea of a wave function. The wave function is not a physical wave in the usual sense, like water moving up and down. Instead, it is a mathematical description of the probabilities of where an electron might be found. This wave spreads out, evolves, and can interfere with itself, just like ordinary waves. But when a measurement is made, the electron is detected at a specific location. The wave, like description, gives probabilities. The particle, like event, gives a definite outcome. This dual nature is not due to imperfections in instruments. Even with the most careful control, the behavior remains. If detectors are placed at the slits to find out which path the electron takes, the interference pattern disappears. The electron then behaves more like a classical particle, going through one slit or the other. The act of measuring the path changes the outcome. This shows that wave and particle aspects are not just hidden features waiting to be revealed simultaneously. The type of experiment performed influences which aspect becomes visible. The wave-like character of electrons also explains why they form patterns in atoms. Electrons do not orbit the nucleus like planets around the Sun. Instead, they exist in standing wave patterns called orbitals. These patterns arise because only certain wave shapes fit consistently around the nucleus. The allowed shapes determine the energy levels of the electron. This is why atoms emit and absorb light at specific colors. The electron's wave nature sets the rules for how energy is structured inside atoms. At the same time, the particle aspect remains essential. Electrons carry a definite charge and can be counted individually. In electronic devices, currents consist of flows of individual electrons. In detectors, each electron leaves a distinct signal. In chemical reactions, electrons are transferred from one atom to another in discrete amounts. The particle picture helps explain these localized, countable events. Wave-particle duality challenges the idea that physical objects must fit neatly into classical categories. Instead of asking whether the electron is truly a wave or truly a particle, physicists accept that it is a quantum object described by a framework that includes both behaviors. The classical labels are approximations that work in certain situations. At small scales, a broader description is needed. There is also a deeper layer. In quantum field theory, the electron is an excitation of a field. Fields can naturally support wave-like behavior. At the same time, excitations come in discrete units, giving rise to particle-like events. In this picture, the duality is not a contradiction, but a reflection of how fields behave at the quantum level. The electron's wave aspect comes from the field's ability to spread and interfere. The particle aspect comes from the quantized nature of the excitation. This dual character has practical consequences. Technologies such as electron microscopes rely on the wave nature of electrons, which allows them to resolve structures smaller than visible light can. The interference of electron waves reveals details of atomic arrangements in materials. At the same time, electronics depends on controlling streams of electrons as discrete charge carriers. The wave-particle duality of the electron also shapes our understanding of certainty and possibility. Instead of predicting exact paths, quantum mechanics provides probabilities. The wave function evolves smoothly, but the results of measurements appear as specific outcomes. This blend of smooth evolution and discrete events reflects the dual nature at the heart of the electron's behavior. In a quiet sense, the electron's duality invites us to loosen our grip on rigid categories. Nature, at its deepest level, may not be built from objects that fit our everyday intuitions. Instead, it may be structured by principles that allow entities to show different aspects depending on context. The electron, sometimes wave, sometimes particle, moves through the universe with this subtle flexibility. As we rest with this idea, it becomes less like a paradox and more like a feature of a richer reality. The electron is not switching between two separate identities. It is a single quantum entity whose full description includes both wave-like and particle-like properties. Our experiments highlight one or the other, but the underlying nature encompasses both. In the stillness of reflection, the electron's duality can feel almost like a metaphor for how the universe blends opposites. The solid and the fluid, the discrete and the continuous, the certain and the probable, all meet in this tiny participant of matter. Through its quiet, consistent behavior, the electron shows that reality at small scales is not confined to familiar shapes of thought. Instead, it unfolds in patterns that are at once precise and gently mysterious, where waves and particles are not rivals but partners in the deep structure of the physical world. When attention settles on the basic properties that define the electron, two stand out with quiet clarity: its electric charge and its mass. These features may sound simple, almost like entries in a list, but they shape an enormous range of physical reality. From the glow of a light bulb to the structure of atoms, From magnetic fields around planets to the signals traveling along nerves, the electron's charge and mass guide how it moves, how it interacts, and how matter itself takes form. Electric charge is one of the fundamental properties in physics. It describes how particles respond to electric and magnetic fields, and how they influence one another. The electron carries a negative electric charge, and every electron carries exactly the same amount. This uniformity is remarkable. No matter where you go in the universe, an electron's charge is identical. This consistency allows the laws of electricity and magnetism to operate the same way everywhere, giving the universe a kind of dependable structure. Charge creates forces. Opposite charges attract, and like charges repel. Because electrons all have negative charge, they repel one another. At the same time, they are attracted to positive charges, such as those carried by protons in atomic nuclei. This balance of attraction and repulsion shapes the architecture of atoms. Electrons are drawn toward the nucleus, but do not simply collapse into it. Their motion and quantum properties create stable regions around the nucleus, forming the electron clouds that define atomic size and chemical behavior. The strength of the electron's charge also determines how strongly it interacts with light. Light is an electromagnetic wave, and its interaction with matter depends on electric charge. When light strikes a material, it pushes and pulls on electrons. These motions can cause absorption, emission, or reflection of light. The colors we see, the transparency of glass, the shine of metals, all arise from the ways electrons, with their charge, respond to electromagnetic fields. Charge also enables electricity. In a metal wire, some electrons can move relatively freely. When an electric field is applied, these charged particles drift, creating an electric current. This flow powers devices, transmits information, and drives modern technology. Without the electron's charge, there would be no electric circuits, no electronic communication, no familiar use of power. Alongside charge, the electron's mass plays a crucial role. The mass of the electron is very small compared with that of protons and neutrons. This small mass allows electrons to respond quickly to forces. They can accelerate easily in electric fields, making currents possible. Their lightness also influences how tightly they are bound in atoms. Heavier particles would behave differently, altering the scale and stability of matter. Mass connects to inertia, the resistance to changes in motion. Because electrons have mass, they do not instantly change speed when forces act. This inertia affects how they move in materials, how they spiral in magnetic fields, and how they contribute to the behavior of plasmas in stars. Even though the mass is tiny, it is not zero, and this small value is essential for the balance of forces in atoms. The combination of charge and mass determines the electron's motion in electromagnetic fields. A charged particle in a magnetic field follows curved paths. The curvature depends on the ratio of charge to mass. For electrons, this ratio is large because the charge is fixed and the mass is small. This leads to tight spirals and rapid responses, behaviors used in devices like cathode, ray tubes, and particle detectors. In atoms, the electron's mass influences the scale of quantum effects. The allowed energy levels of electrons around nuclei depend on their mass. If electrons were much heavier, atomic sizes would shrink, and chemistry would be dramatically different. If they were much lighter, atoms might be larger and less stable. The actual value of the electron's mass helps set the dimensions of the microscopic world. Charge and mass also enter into energy. According to relativity, mass is a form of energy. Even a particle at rest has energy due to its mass. For the electron, this rest energy is small on everyday scales, but significant in high-energy processes. When electrons and their antiparticles, positrons, meet, their mass can convert into photons, demonstrating the deep link between mass and energy. The electron's charge is quantized, meaning it comes in a fixed unit. This